Okay, so up to this point, we've talked about the kind of the mechanics of the instrumentation system inside of an airplane. We've talked about gyroscopic instruments that use suction. We've talked about navigation instruments, all kinds of things. The reality of it is that nowadays the new aircraft are coming out more and more with instruments like this that are glass panels that have all your flight data integrated, so that way there's only one place to look, and that there's a good reason for that. Like, one, it makes life a lot just easier on the pilot, reduces pilot workload fairly significantly. It's safer, so instead of doing all of this and looking around, you're looking at one spot. And you'll see with when we get talking about heads-up displays, you're looked up out the window at where the plane's going, and all that data is coming in right in front of you. So that way you don't have to do anything looking down, to where it decreases the chance that you might look off to the side and miss something critical and then have an accident. Now, what we're going to do in this class is that we're just going to start kind of like in the history of displays, and we're going to build up and let you see all the different types of things that you may see out there in the field. Not every plane is going to have a brand new Garmin 1000 or have a 737 MAX 9 display system that has everything integrated in it. You're going to see a lot of older things. So if you look at this, like the Learjet has old round dials that have just like one data point integrated into them, next to a Garmin 430 that is fairly modern. It's not the latest and the greatest, but it is. It's going to give you that GPS capability and that navigation capability, and integrated with the autopilot and all other good stuff that you would want in a modern private jet. So as we progress on, just keep in mind that you don't need to be an expert in any one part of this, but you need to be familiar with it, so that way you know what you're going to be getting yourself into. The other aspect that's coming up is that we're going to talk a lot about the 737 MAX. Now, there's nothing necessarily special about the 737 MAX. It's just what's available. Now, it will generally be representative of all the other heavy commercial airplanes that are out there. They're not all exactly the same, just like the 737 MAX, but generally speaking, most of those systems are very, very similar. They might have a different kind of architecture software-wise. They might have a different arrangement, or might have like their own little nuances, but for the most part, they're within the bounds. It's kind of like a small four-door car is a small four-door car. It doesn't really matter if it's a Golf or a Civic or whatever. They're all kind of the same, but they all have their own personalities, and they all have their own perks and their own drawbacks. So come along for the electronic displays class. All right, so this is a 6-pack. Now, it gets its name from the number of dials that you're looking at, 6. So we're just going to start from the top left, and we're going to work our way, clockwise, and just talk through every single one of them. So the first one is probably, if you're a private pilot or someone that's flown, you know how crucial it is, but that's your airspeed indicator. Now, there's 3 arcs that you see around it. White will tell you, hey, look, this is a flap operating range, is typically what white indicates. Green is a normal operating range. Yellow is like, hey, look, you're kind of getting up there. And then red is like, the do not exceed speeds of V&E. But that just, all it really does is tells the pilot, hey, look, this is how fast you're going, relative to the air. Now, some things can change that based on headwinds and things like that we've talked about in other places, and we will talk about more in the future. But that's what all the airspeed indicator indicates. Next is go to your right with a little airplane on it. That's your turn and bank indicator. So that will let you know like how much the airplane is rolled, and that ball will swing back and forth based on whether or not the turn that the airplane is in is coordinated. If you have a turn where the left side of the tail is kicked out and it's out of like the slipstream of the airplane, that ball will roll to the left. And so what the rule is you step on the ball if you're flying. You'll step on the ball, and that will bring the airplane back into coordination and put that ball back into those little hash marks that you see there. And that's just to help you make good, solid, coordinated turns. Now, the other 2 tick marks on the outside, notice that the tick marks where the wings are level at, that means that, hey, look, your wings are level, period. Then the other tick marks or indicate that, hey, look, you're in a standard rate turn. So if you're in instrument flying, you're looking out of the windshield and all you see is clouds and there's nothing to reference anything on, you can turn the airplane until that little wing will go down to the tick mark that's below the horizontal tick mark, and you'll know that you're in a standard rate turn. And those standard rate turns are kind of like a known mathematical fact that you know that, hey, look, if I'm making the standard rate turn at this airspeed, this is how long it's going to take me to go around, and so that way you can navigate whenever you can't see outside of the airplane. The next one over is your altimeter. We've talked a lot about the altimeter. This one's a little bit unique. It's not your standard altimeter, but that is what that is. We won't spend too much time on it. Underneath is the vertical speed indicator, the VSI, that lets you know like how fast the airplane is either climbing or diving. And so if you know you want to be at a certain altitude at a certain time, you can set the VSI up to tell you, hey, look, like we need to go down 2,000 feet in the next minute. Well, you just nose the plane over or reduce the power until you see that needle go over to 2,000, and you're gonna make your altitude time hack. To the left of that is your vertical horizon. It's your big gyroscopic powered instrument that allows you to say, like, it says, hey, look, this is the rate of the turn that we're in. This is the rate of the bank that we're in. This is if the nose is pitched up or pitched down. All that good information. A lot of the information from that you can kind of glean from the other instruments kind of integrated into the artificial horizon. Your VSI will basically tell you what your pitch is, more or less, and there is some nuance to that with power settings and things like that. But those power settings are also indicated on the next instrument to the left of that, the RPM gauge. Like it says, like, hey, look, this is what our power setting is at, and this is what the plane's going to do because of it. And then there's a little hour indicator to let you know how many hours the engine's been operating. But that's a six pack right there. That's whenever they talk about a six pack, that's what they're talking about. Those six instruments. All the other instruments that are out there are generally not super crucial for flight. They can be super handy. They can be really good information to have to help manage things correctly and troubleshoot things whenever they go wrong. But these are the six instruments that you absolutely need to be able to navigate and operate an airplane safely. All right, so the first iteration of digital flight displays or electronic displays actually didn't have anything to do with performance, but it mostly was centered around navigation. So you'll see in older GA airplanes these big brick GPS units because they were the kind of the first items to come out. Now this one is GPS Map 396. It's integrated with all kinds of other things. It's very modern. Well, in terms of those old bricks, at least. But the original ones was it was just navigation. Then you eventually got to where you had like airport information on there. You had to load on a little SD card and you put them in there. And then as time progressed on, you got color displays. It started taking in weather data, and they got pretty sophisticated before they they're not necessarily obsolete. You'll still see them used in different places, but for the most part, the panel has replaced them, so that way you don't have to mount this thing on the like your control yoke or inside of the on the instrument panel itself. Instead, now the panels are part of the instrument panel and has all the same information. But these really were kind of revolutionary because all of a sudden you didn't have to use radio navigation like you used to, or navigating by compass or anything else. You could navigate strictly direct to where you're going via GPS, and it made life a lot simpler on the pilot. It also made flights a lot faster because instead of having to track a VOR and then turn and then track the next VOR or do something like that, you could just get a straight line, flight path directly to where you're going, and you didn't have to worry about like losing a VOR signal or anything else like that. And I just realized we probably haven't talked about what VORs are yet because we haven't done our navigation class, but we will talk about it in the future. Suffice it to say that these were really a big step forward. About the same time that you were getting GPS units like TomTom stuff into cars, these guys came out, and whenever these guys came out, it really helped you know about what time you're going to arrive and how fast you were going and all the kind of things that we're used to now. Back in the early 2000s, This was a premium feature to have in your airplane, but it was the first electronic flight instrument or flight display that existed. All right, so this is a Garmin navigation system 430. This is like one of the first Garmin in-dash GPS systems that came out. Now these were a big step forward. For one, you didn't have the big brick on your control yoke that like you're trying to fly and it's bouncing around and going all over the place. But the big kind of step forward is how integrated it was. If you'll notice on the top left hand side of that LCD screen, those are radio frequencies that you could tune the radios with the unit now. Whereas before you had like the GPS and then the unit, your radios on a different spot, and you had to fiddle around with both of them. Now you have a integrated display that tells you where you're at and will also let you control the radios. Another thing, if you'll notice, there's like the direct button right there. You can also start to plug these to interface the autopilot in with the unit itself. So now you get up to your whatever your flight level's at, and you can turn around and just plug in what your next waypoint is, and the autopilot says like, okay, I see the GPS is plugged to that, and off you go, and like it will just go where you tell it to. So also now it becomes a lot more less about flying, more about like just airplane management, just telling the airplane where to go. But that was kind of the next big step in electronic flight displays. It was these units, and there's several of them out there, and they're still widely used in aviation. They haven't gone away. They're still out there because they're a lot more affordable than some of the more modern big glass panels. But they definitely are on their way out because the more panels that come in, the more these things start to get kind of marginalized. Okay, here's our first real modern panel. This is a Garmin G1000. It was for a long time the standard for electronic flight displays out there. Now, it's since slowly kind of been eclipsed by other glass panels, but the technology is very similar. The newest things are touch panels, and a lot of it's kind of focused not necessarily on being innovative with the display, but rather trying to reduce the cost of the display. And you see people like Avidyne and Dynon come in there and try to do the same thing that Garmin does, but do it cheaper. Notice on this one how robust the information has gotten at this point. Like we started off with just those old big brick units showing you where you go. Well, now we have flight data. So notice that the horizon there, that's artificial horizon with your altimeter and your airspeed indicator integrated into it. You have your navigation data with the little VOR guy down there at the bottom, and you have all your engine instruments as well on the left hand side. It tells you even individual cylinder head temperatures, so that way if you start to see that your engine's running a little hot, you can tell exactly where it's running hot and you know where to go investigate. And then up top is still all your radio management stuff. You can still tune the radios and manage the autopilot from the display right there, because it's all kind of an all-in-one. And a lot of like smaller GA planes, you'll start to see that they may have a few standby instruments, maybe, but a lot of the newer ones have just the panel and the panel alone, because the panel does so much. There's just no need to have so many other instruments out there unless you just want lots of redundancy. And so there, that is kind of your panel systems. Now let's look at what it looks like whenever you get it on a modern commercial, heavy commercial aircraft. All right, so this is the inside of a 737 MAX. Now you'll notice there's no round dials. The closest you have is that ISFD that we're going to talk about here in a little bit. But there's 4 panels. There's 2 for the for the co-pilot, and there's 2 for the first officer. Those panels are really not that heavy. They're not that big. And they go in with just little bitty screws that are about 6-inch pounds a piece. There's not a lot holding them in there, and they just plug up to the rest of the instrumentation system. Okay, so this is the captain side, or the left-hand side, so the pilot side of the airplane. And notice that there's 2 different screens. Now, the knobs that are on the bottom, they're just below those gray knobs right there. Those will allow you to put all the information on one screen, all the information on both screens, so on and so forth. Turn one of the screens off. You have a lot of options that as the pilot, to choose on how you want your information displayed. If you'll notice that that left screen there, you have the artificial horizon above, the navigation like set up below, and then looks like you have a clock with some other information off to your left hand side. You can have that too. On the right hand side, you have your terrain awareness map with a lot of engine data that's coming up. This is all very customizable on a modern screen, and it replaces all of the dials that used to be there. Whereas the old dials that were fixed and you just had the information that you had in front of you all the time, this thing allows you to turn some information off because you don't need it, and then turn other information on when you do need it. And this is definitely the way that things are going. If you look at the new Gulfstream cockpits, they're all one big glass panel, and even the buttons have started to be integrated into these displays. All right, and then this is the first officer side. Notice that the cutout there is moved to the left, so that way it'll accommodate the throttle quadrant. But it's effectively the exact same thing. You still have the same display selection knobs there that you can flip whichever way you need to get the display correct for your preferences. But yeah, so that's the first officer side of a Mac. Okay, so this is how those screens get their data. And we're going to show another slide here in just a minute that kind of talks about where all that data comes from, how it gets integrated, and then pushed out. But the two boxes I want you to pay attention to right now is the DPC-1 and DPC-2. Now, those are your digital processing computers 1 and 2. Notice that DPC-1 is your primary digital processing computer that feeds all four screens. However, you have a backup DPC-2 that will turn around and only feed two screens. Now, learning systems like this is extremely important because when you get on these heavy commercial airplanes and you have a fault, you don't want to necessarily only go and say like, oh well, the screen must be out because the screens aren't coming on. You can actually set a setting up so that way you turn off DPC 1 just to check and see if DPC 2 is actually sending the right data to the screens. And so you might just be a switchology problem that you're troubleshooting and it's not anything's broke at all. It could also be that a DPC has failed or faulted out, and you'll need to troubleshoot them. One of the easiest ways to troubleshoot things like this is just go down to the eBay, pull both of them off, swap them, and see if the issue travels. If all of a sudden all the screens come back on or none of the screens come back on. And that helps let you know if the box is bad or if it's something else. If it is the wiring, or in this case it's fiber optic lines, or is it the screen itself. And so like understanding the hierarchy of how all of these different components interact with each other allows you to think tactically about how you proceed as a troubleshooter. So this is where like your systems manuals, your wiring diagrams become very, very, very important to help educate yourself on any plane that you're working. And that allows you to isolate problems quickly and act quickly so that way you can get that plane back up in the air. Now, one of the things to remember is that the Max's display system came out before touchscreens were really kind of widely available, or at least they were designed before it, and then implemented while those other displays were starting to come out to the general consumer. That being said, the way that we control them are going to be your lighting control module and your instrument switching modules, which is like the very top for both FO and Captain. The switch cluster that you see at the very top, and then the one that's in the bottom in the middle. The other two down there are the electronic flight instrumentation system control panels, both left and right, and they correspond to the captain and the first officer. And so those two will allow you to switch screens. We'll turn around and tell you like, hey, look, put it on the approach mode or map mode or whatever, and allow you to navigate the screens that the display system will allow you to see with relative ease. Then you have a multifunction panel in the middle that also allows some customization of what you're seeing. So this is all really important whenever you're trying to understand the state of the plane, or understand a fault, or even just navigate them for general maintenance. If the maintenance menu calls you to do one thing or another, you want to be able to be the type of person that can sit down in that cockpit and very seamlessly navigate to exactly where you want it to go. And the only way that you do that is simply by getting in here and playing with it and understanding how to get to where what page you're looking for, and so on and so forth. Now, up to this point, we've only talked about like how to manage the displays, but not where all of the information is coming from. Now, every airplane is a little bit different, and some airplanes will have displays. Like if you think of like an RV-10 or a Cessna 182, they might have like a Garmin 1000 in there. There's like a little SD card that has a lot of your maps and things that are loaded onto it, and then like live weather data comes over the ADS-B network or some other means depending on the model. On the Max, we use a lot of the network file server, the NFS, extensively for a lot of data that gets displayed to the pilots. So let's just start at the top of this graphic, and we're just going to work our way around as an example of some of the places where we can get data from. So one is the portable maintenance device. A lot of times those the runway calculations, the performance calculations, all that kind of stuff is going to come from data that gets uploaded by a laptop from an avionics technician on the ground. You'll just plug up to the NFS and then push the data from the laptop, which is coming from some other place, and then up onto the NFS itself, and then the airplane will be able to access it as it needs it, and effectively turning the NFS into like an SD card, just like you would see on, like, on a G1000 or something like that. Now, you can also get information wirelessly. Different. There's different situations where that would be useful, and you can see you're definitely going to see more and more of that in the future. You have the FMC and MCDU on there. The FMC is the flight management computer, so there are ways to plug up or input data from your flight plan into the FMC, and then push it to the rest of the plane, and you'll see a heading that you're going to fly or a coordinate you're going to fly go from the FMC to the NFS to the display itself. SATCOM is another one. You're going to see more and more of this in the future, where teletext is becoming bigger and bigger, to where instead of using the radio, they're just going to text the airplane, and that's going to come from SATCOM. There's also other information. So let's say you're over the Indian Ocean in the middle of nowhere. Being able to get satellite data allows you to remain connected to the rest of the world. Whenever the only other option would be through HF radio, kind of arcane, but not you don't have to rely on it as much in the modern era. Now this down here where it says flight deck, printer one, and displays, that is saying that the NFS feeds those displays, and there's actually a flight deck printer that will print out different items that you may need. Teletext being one. As a mechanic, you're going to use it a lot to sign off jobs that you'll run some sort of operational check on some system somewhere, and then on the display it'll give you the option to print. You can print that, and you can take it down to your quality control person and let them say that you actually did what you said you did, and they can feel comfortable signing off that work. Electronic engine controller is another one. This is called EECs. They're basically just monitoring all things engine and pushing that to the NFS to catalog it, then codify it in a way that it can get displayed via the DPC-1 or DPC-2. Enhanced ground proximity warning computer. That's basically your hey, don't run this thing over box, and it also goes to the NFS and then onto the displays. And then lastly, the DFDAL, the Digital Flight Data Acquisition Unit, which is basically all of your digital flight information goes onto the DFDAL. This is actually your flight recorder. Whenever they talk about like the black box, this is the thing that's recording a lot of the actual flight data, and then it goes on to the NFS and then up to the display. So like a lot of your airspeed, altimeter, all that things are going to get routed through the DFDAL. Now, why is this important to know when it comes to like digital displays? Well, it's really simple. Like if you're trying to troubleshoot an airplane and trying to understand, like why the things, if the pilot's saying like, hey, look, the airspeed is off, or hey, look, it said that it kept giving us like these faults or these warnings, or it said we're at 40,000 feet and it's giving us warnings about hey look we're about to run over a antenna or something ridiculous. Then you know where to go look. Like it's despite the fact that it's a very big and complicated airplane, these hierarchies actually make it very, very easy to troubleshoot because that data is coming from some place and you can track down exactly where it's at. You may not know exactly what's wrong with, say, like the diff dial or what's wrong with, the SATCOM or whatever. But like a lot of times it's easy to kind of like just eliminate a lot of things and go from there. And you also, if you know how these different systems interact with each other, and you're starting to see like a lot of different problems, then it might just be like one central point has gone bad, and you take that central point out, replace it with a new part, and boom, all these problems just work itself out automatically. The NFS is like a classic one that can be not seated correctly, or it'll have some sort of corrupted data, or any number of things, and it'll affect all of these systems in reverse as well. So it's something to keep in mind, to learn your systems and learn the architecture in which they interact with each other, because that will help you become a master troubleshooter, and that's what most employers want. All right, now that we know how to manage the displays and we know where the data is coming from, let's talk about just reading the displays yourself. Let's say you're flying along and you're looking at this screen and you're wondering, like, what information is it actually trying to communicate to me? Well, if you're looking at the left hand, we're going to go to the left outboard primary flight display on the top left hand corner of that. It's going to give you a flight number that says 737 Max 01. All right, and that tells us, hey, look, that's our flight number. Now, we haven't really talked about the way the airlines operate, but flight numbers are different than tail numbers. But if you go down a couple of data points there, you'll see November 178. Looks like 5 Bravo on my screen. If you can see it, and that's the tail number of the actual airplane. Now, to the right is a clock. Now, that clock is a timer. It's not an actual clock. Now, that's important because during like instrument operations, knowing that, like, hey, look, like you're going to hold in this area or you're going to turn here or whatever, will allow you to make really precision flight, maneuvers with basically just a stopwatch. You know that if you're in a standard rate turn for so long, then this is how, where you should come out at. Below that is going to be your actual time and date. That's going to be really, really important. And then your elapsed flight time to let you know how long you've been flying. So that way, let's say you had a FQIS failure and you want to know how much fuel's on board. Well, if you know that you've been at 100%, power for 3 hours, and you know how much 737 Max burns for per hour, that will help you kind of dial in exactly how far you have left to go on that bag of gas. All right, so then the looking to the right is your artificial horizon. Now, we've talked about this a little bit, but let's kind of like break this down. I'm going to put up a graphic here in a minute that will help you explain it a little bit better. But on the right, there's two ribbons, and then the actual artificial horizon itself is nested in the middle. On the left ribbon is going to be your speed, and on your right ribbon is going to be your altitude. And now notice on the very bottom it's set to 2992. That's going to be your standard pressure day. So you can change your altimeter setting on this as well. And then your artificial horizon will allow you to say like how many degrees up or down you're pitching, and then it'll also tell you how many degrees of bank that you've got in there. Now, there's another interesting little tidbit on this that, like, for instance, the little purple dot with the two white dots on either side of it on that artificial horizon screen, that's effectively the ball that you're going to step on. That's your turn and slip indicator that's been integrated into this. If you go up the display, you'll see ILS in the top left hand corner. That's telling you that it's on instrument landing system. That's what it's dialed into. So that way the what the navigation system is tracking. There's all kinds of interesting information that's built into this. The bottom screen, you'll see on the bottom left hand corner it says ADF2. That's Automatic Direction Finder 2. That's where it's getting that little blue arrow on the compass rose arc. That's where it's saying like, hey, ADF2 is saying it's this way. So if you're trying to fly to an ADF, that's where you're at. The little purple dot, that's your heading bug indicator. So a bug, which we're going to talk about here in a second, basically just allows you to customize that arc and say like, hey, like I need to fly this heading. I want to put a reference point on there, so I don't have to look down and try to figure out where heading 090 is every single time. I can just look at the heading bug and then fly there. And I know that the turn, or that I'm flying directly to it. If I take my little white chiclet and I nest it inside of the little fork heading bug indicator. If it's perfectly lined up, like you were shooting a rifle, well then boom, like you're going exactly where you need to go. All of this information used to be displayed on a sea of instruments across an entire dashboard, and so like, you'd spend all your time looking at the instrument panel trying to figure out like where you're at, where you're going, then look up, make sure you're not going to hit anything. Okay, cool, and then you go back down. Well, now with this, it's all in one stop shop. But once you kind of train yourself to look at the display, then you can ingest this information rapidly as opposed to trying to hunt and peck, try to figure out where everything's at. This is a great step forward for avionics, for aviation safety, and just general pilot workload reduction. There's a screen you can flip to. Notice that it gives you two options. Here's like the full screen. Then you can only put on half of the display if you're trying to like watch your flight instruments and watch your instrument approach screen as well. And that's what this is. This basically will tell you, hey, look, are you on approach? Are you navigating correctly? That the green font in the top right hand corner says ILS 1. So it means the instrument landing system 1 is what the data source is. And you can change that data source on the EFIS switch cluster down there as well, the control module that controls all this stuff. And you can put it on GPS WAS, you can put it on ADF, you can put it on a menagerie of instrument systems depending on what you're trying to accomplish and what your preference is. This will basically tell you, hey, look, the dotted line with the little heading bug up top tells you where you want to go, whereas the solid line tells you where you're heading. So this guy's basically mid-turn. He's already turned, and like he's waiting for his course line to catch up with him. On the top left-hand corner, it's going to give you your wind data. It says like, hey, look, it's 325 at 1.5, so it's decent wind. It's got a tailwind. He should be landing upwind, but for a 737, you're talking about like 60,000 pounds or more of airplane. A little 15 knot wind's not really going to be that big of a deal for him. But yeah, all this information is just integrated. You have your heading that on your heading bug right there. He's flying to 133, so it tells the pilot all the information he needs to know about his approach right then and there. Now, if I was this pilot, I'd probably be using the half screen. I'd be using my flight data off to the right hand side to make sure I was like making a nice, easy approach that we're going to land so that it's soft and doesn't, jar grandma and knock her dentures out or anything crazy like that. Let's look at another screen. All right, so this is a VOR. VOR stands for VHF, Omnidirectional Reference. It basically is kind of like you can think of it like kind of a homing beacon for now. We'll get into exactly what it is, later on. On the bottom left-hand corner of the screen, it's going to say like VOR 1. It says Seattle. VOR 2 is, that's Payne Field up north of Seattle. Every VOR has its unique identifier. You can tune into the VOR frequency itself with your comm radio and actually listen to the Morse code that will just go dee 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 dee, and it'll spell out CTAC or PAE. So that way you know who you're listening to. If like let's say you forgot your map and all of a sudden you're like, oh, here's a VOR, and you can actually like tune it into and like understand exactly who you're tuned into, and that kind of helps you determine where you're going. Other than that, there's not really a whole lot that's just totally different about this screen. You'll notice on the right hand side there's some different bugs. Those are largely going to be focused on flights. We won't get into it a whole lot of detail until we get to our navigation class, and we'll start to kind of unpack them. But just know that this is a VOR screen for a MAX, which is a proxy to just about any heavy commercial aviation aircraft that's out there. They're going to be very, very similar to this. Okay, here's your flight plans screen. So this is kind of the plan as you get on board. Part of your pre-flight as a pilot, you're going to turn around and say like, hey, look, I'm going to fly to this place, then I'm going to fly to that place, then I'm going to fly to this place, then I'm going to fly to that place. And a lot of these are going to be waypoints that have a 4-digit identifier code that you can then tell over the radio to flight service, and they'll have it in your flight plan as well. The other good thing is that you can input these on the display and then turn the autopilot on. Autopilot will fly, that heading and that altitude to to every single place and then turn it as needed. So you can see how it becomes like really really advantageous to be able to input it and be able to sit back and kind of just relax as the plane just kind of takes care of itself. And at that point, you're just talking to ATC and then managing as needed. Now, there's not just a whole lot to talk about this. It's a largely kind of flight focused, and we'll get into a little bit more in when we get to talking about autopilots, which is its own class. But just know that's what's happening on the Max display screen. Once again, just a proxy for just pretty much all aircraft and all heavy commercial aircraft for sure. Okay, here's what the screen looks like in map mode. A lot of that gray or kind of brownish looking stuff, that's terrain. And then you have your approach plates. That's where you're going to fly in and approach an airport in a certain way. They're in magenta. And then you'll see weather get overlaid on this as well. And then you have those options to set all this stuff up on your EFIS or display control. The red is that you see on the kind of left hand side there. That's stuff that is dangerous to the aircraft, and then the other is just for awareness that, hey, look, you're flying over terrain, which can affect the wind currents and so on and so forth. There's another feature of the Max. If you notice on the bottom, that's giving you the ground proximity awareness, letting you know how far off the ground are you. Are you in danger of running into something, or are you like way too high, or whatever? Kind of just like an added bonus for pilot awareness, but that comes up on the map screen. Okay, so we've talked through a lot of the different flight displays that you could see on a 737 Max or any other digital display, really. But let's talk about the ISFD. So this is the Independent Standby Flight Director Indicator or display, depending on which one you're looking at. It basically gives you everything that you possibly need to fly to get it on the ground safely, to include altimeter, ground speed, decision height, radio altitude, all the good stuff, all integrated on one small display. Now, typically, this display is going to be drawing from its own data sources. It'll have an internal battery, if not its own external power source, or a way to be powered from multiple power sources. So that way, no matter what happens, the airplane effectively just has to crash or fly for a long period of time with no power being generated whatsoever to get this guy to be deactivated or be wrong or anything else like that. Generally speaking, your ISFDs will always be just spot on and kind of like your little standby friend, no matter what. But notice all the different information that gets integrated onto this one display, as opposed to the old round dials that have just one little bit of information and they take up all this real estate, and they cause you to have to look to understand where your RPMs are at, and they'll look over here to see where your heading's at, and then they'll look over here and see what your radio is tuned to. The advantage of an electronic display truly is that it takes all of that information and puts it in one spot, so that way in an instant you can look at one display and know exactly where you're going, what you're doing, who you're talking to, all that good stuff. Okay, so what do we do whenever there is a problem? Something has failed. Well, how would we know that something has failed? Well, lucky for us, all of these line replaceable units, or LRUs, which is basically the computer systems that run these displays that you're looking at right now, have a system on board that's built into them, very integrated, to test it to see if it actually is working or not. And that's called a byte test, or a built-in testing test equipment. And depending on if it's byte or bit, it just depends on the manufacturer, year, and all that good stuff. But essentially, they all work the exact same way. You can walk up to that Rockwell Collins box right there and just press test, and the maintenance manual will tell you like if you just press it, or you press and hold for so long, or whatever, and you'll get a series of light flashes. And the maintenance manual will tell you, hey, look, like whenever it is like flashing this or flashing that or flashing this color combination, or maybe it's alternating red and amber, red and green, or whatever, then you know that this is the fault that you have on that box, and you can either take it out and tag it and get a new box, put it back in there, or maybe there's some sort of process or procedure that you can undergo to reset that Collins box, so that way you can keep on using it. But either way, like part of your pre-flight will be to run those bit checks or byte tests or whatever the preferred nomenclature is for them, and to make sure that the box itself is working. Now, just about every LRU has some version of this. Sometimes it's like a push with like little LEDs on it, just like you see on this one, and sometimes it'll be like a little circular, what they call like flags or chiclets, that will, like, if there's something wrong, it'll turn white, and then you can spin the display to reset those flags so that they go back to being black again, and then you rerun whatever task the LRU was doing, and if it faults again, then you probably have a bad box. Sometimes things just happen, and they will fault out, and you can reset them, and they're okay. And sometimes the box itself is back, but that is a byte. Okay, so on the Macs, there are a series of what you could call byte tests, or a way to run byte tests. And then it's on a page called the maintenance data pages. Now, these data pages will give you an just unbelievable amount of information about what's going on in the airplane, even down to the various states of certain pins, or certain wires, certain airing connectors on the airplane. It'll let you know, hey, look, this one's in a high state, this one's in a low state, this one's on, this one's off, this is a 1, this is a 0, to every single pin on every single connector, anywhere on any of the data bus lines, which is pretty incredible. Like, it really does break down a lot of information for you, and this is really helpful with troubleshooting. So that way, if you want to know, like this, system is failing, and you're like, I can, get on the wiring diagrams and figure out that like the source of this failure should be right here. And if you go to that on the maintenance data pages, it'll tell you, hey, look, this one's in a low state. Well, it should be in a high state. Okay, well that's a problem. Like, the question is like, we know the connector is the issue, or that little area is an issue, not necessarily the connector. And you can kind of really hone in on what the problem is really, really fast. And that's all from using a modern byte test, or maintenance data page. Other aircraft like the 87 also have digital circuit breakers. You can add that layer to being able to troubleshoot more effectively. You can get on there and close certain circuits and open other ones. But ultimately, the real troubleshooting is going to come down to running these tests, these maintenance operational checks or byte tests, from that maintenance data page. You're going to turn around and say like, hey, look, do a functional check on XYZ system, and it'll run through that check and tell you if it passes or fails. Now, that's not technically a byte check itself, because but it's still built in, and it's being prompted by you, and that's something that you'll do on a regular basis. Now, there's another term you'll hear referred to called EFIS, or Electronic Flight Instrument System. EFIS, all it is basically another way to say like this, electronic display system that we've been going on about. It's taking all of that flight instrumentation, digitizing it, and displaying it in a way. Now, what you have in front of you on the screen is the FMS system from a 737. Yeah, and these kind of go back a pretty good ways. They've been in 737s for a hot minute. But this is a way to also display information and also interact with the plane. So you can put in your your different GPS fixes. You can put in radio calls. You can text the tower over this stuff. Anyways, these FMS systems are pretty robust, and they were kind of like one of the first iterations of digitizing the flight deck. You'd still have these old FMS computers, while you had round dial gauges in some of the older 737s. But like, they still exist, and probably will exist for a little while. They haven't quite been replaced yet, but I want you to be aware of them. It's not just the displays, but it's also these computers that are on the center pedestal. Another one that will come up is called ICAS, or the Engine Indication and Crew Alerting System. Essentially, all ICAS is it takes all of the engine data and puts it on a single page for you. Um, every flight deck is going to have some variety of this, especially on modern aircraft. But they'll all look very different depending on the make, model, type, and age, and just the preference of the person who ordered the aircraft or assembled it. ICAS is it's not necessarily new, but it really has seemed to kind of take a life of its own over the past couple of years with a lot of this engine monitoring that's come along. I can remember back in 2009, 2010, whenever the Army first started putting in vibration monitoring technology with the IV hum system in the OH-58, and they were doing similar things with the Apache and the Black Hawk and Chinook, and that all got piped into kind of the ICAS like system that was on board of the OH-58 that did a lot of engine health monitoring, a lot of airframe monitoring, and helped trying to use predictive analytics to forecast where what was going to go bad when, so that way you could minimize downtime, which is kind of like the ultimate goal of any maintenance operation, is to try to like minimize downtime as much as humanly possible. Okay, now let's talk about HUDs, or heads-up displays. Now, this is the cockpit of the Me-262. It's the first ever jet fighter developed by the Nazis back in World War II. If you look just above the instrument cluster, there is a little gray box. And on top of that little gray box, if you look and kind of squint, there's like you can see a piece of glass that's canted back, kind of at a weird angle towards the pilot's face, and that is the first ever heads-up display that was put onto an airplane. Now that HUD went on to kind of set the standard for specifically for fighter jets, but there's other airplanes as well that have gone on to use them. Now, what is a HUD? A heads-up display is basically all of your primary flight instrumentation, your like say your heading, your roll rate, your airspeed, your altitude, all of that kind of primary flight information that allows you to be a good and safe pilot. It's putting all of that on a system that you can look through, so that way you can look at the runway and then see what your airspeed's at. So that way it cuts down the amount of time that it takes for you to detect a non-conformance with the flight profile that you would like to be in, and then make a correction. And that allows you to fly more precisely, more safely, and all that good stuff. Now, HUDs, you can find them on all manner of different aircraft. This is just one example. They're the well, any of your fighter jets will have HUDs placed on their dash. The F-35 has a HUD that's built into the visor of the flight helmet that they use, just like the AH-64 Apache from the Army. They have a monocle that flips down. All that is a HUD that's attached to your head, so that way whenever you turn your head, the HUD is continuously displaying flight information to you, so that way you can look to your left and be flying one way and then decide if you're going to make a turn or not. That in particular system also allows for you to turn the main gun on the front of the helicopter. C-17s, you wouldn't think a big cargo plane, but a C-17 has a HUD, primarily because it simply makes operating the aircraft that much safer. That you don't have to look down to make a flight decision. As time progresses on, you'll see more and more aircraft actually have HUDs, and so you need to be comfortable dealing with them. Okay, here's an example of a HUD that you can buy and put on your like Cessna 172. If you'll notice, it has all that primary flight data on the glass there. You'll have the altitude on the right and the airspeed on the left, and then your roll rate, your pitch, all that good stuff. That's just displayed so that way you can look down the runway and look at the HUD and know exactly where you're going, at what speed and what altitude, and all the information you could possibly need to make a good, safe landing. Now, this is a HUD on this one's actually on a private jet. What you're seeing there is what they call synthetic vision. There are sensors on the aircraft to help look through the clouds and kind of project an image of what the terrain is doing below the aircraft. The most famous one for this right now is actually the F-35. There's other aircraft where you can put that synthetic vision on your flight helmet and then effectively look through the body of the aircraft because there are cameras and sensors picking up what's going on all around it. But the HUD is on this in particular aircraft being projected onto just a glass panel that looks only in one direction, which is by far the most common approach to it. Now, you'll see aircraft at the gate taxi up with these things on. If they're stowed, they generally have kind of like this like little sleeve that goes over the top of them to keep them from getting scratched or dirty or anything else like that. You can imagine these systems are pretty expensive and they don't want to see them get damaged. And so that's what HUDs are. They basically are heads-up displays for the displaying of primary flight information. All right, now let's say we had to do some work on either an LRU or a display. There's a threat to the device called ESD or electrostatic discharge. So now what's that? We've talked about this a little bit before, but we're going to talk about it again. So ESD effectively is the buildup of electrons in your body that are negatively charged that will jump off your body and onto another device to help kind of distribute the amount of electrons that are there. Now, this is no different than lightning. It's basically at a much smaller scale. And so you've all had on socks and kind of like rub your feet across the living room floor and then touch the doorknob and then it spark, or like make a little shock. Or maybe you've even done it to like your sister and like rub your feet across the living room floor and then go behind her and touch her ear and it will shock her. That's all ESD is trying to prevent the shock from jumping from your body and onto an electronic device. Now, most times whenever you're just shocking your sister, it's just good fun, and that's all there is to it. But whenever you're talking about a circuit card, particularly, or something that is attached directly to a circuit card, like say a connector or any sort of wire like that, you can fault the board. You can actually cause it to be burned and be permanently defective. And we were talking about some of these boxes are $100,000 or more. That's the last thing that you want. You want to be able to take care of them as much as you possibly can. So there are certain precautions we're going to take whenever we take out an LRU or a display or anything that has a microcontroller on board to prevent electrostatic discharge from happening. Now, ESD in aviation is especially dangerous because there's a lot of wind going around. So there's always like a lot of friction between your clothes and the wind. They could potentially build up shock. You are going to be around things that are electrified, which will also cause you to build up more electrical charges in your body, and it'll arc and jump. So whenever you go to take off an LRU, what you're going to do is you're going to place this type of device on you. Now, this is an ESD strap. What's going to happen is that that strap there is going to go to your wrist, and that is going to expose your skin directly to a piece of metal. Then on the other end, where there's alligator clips, you're going to pull that alligator clip off, and it's going to have just a single little plug, and that plug is going to plug up onto the aircraft. And the aircraft, especially in the eBay, will have a chassis ground plug or port that's made specifically for those ESD plugs. You'll plug yourself up, and that will ground yourself, so that way any of the potential for electric shock will leave you and go into the airplane, and the airplane's big and grounded, and you don't have to worry about accidentally shocking anything. But that's not all of the precautions that we're going to take. But before we get off this one, like I would encourage you. When you go to work in an avionics shop, these things are everywhere. Grab one of these and put them in your pocket or in your kit, your toolbox, whatever it is that you're wearing or using, that you'll have quick, ready-made access to it. Because this stuff does matter. I mean, a lot of people get really very lackadaisical about it because it's not like the plane's going to explode or anything. It'll be a little shock if it happens at all, and it will affect a very particular part of the board, and then you may even get past handling it and not have any problems. but it doesn't take very long down the line. Somebody's gonna start having this like very weird particular issue, and they can't figure out what's happened. And what's really happened is that you burnt down a component on the circuit card somewhere that only really deals with a very specific set of tasks. So just go ahead and put one of these in your pocket, put one of these in your toolbox, put one of these somewhere that you can readily use it, or even you can wear the strap everywhere you go, and then turn around and disconnect and reconnect the wire as needed if you want to go in that route. All right, so once the component is off of the aircraft, you're going to put it in this ESD bag here. You're going to open it up, slide it in, and close it up. And usually there's ESD tape, so it's like non-static clean or causing tape that you can tape it up, so that way that component is permanently, well, at least for while it's in the bag, it's protected against accidentally shocking it and burning up a circuit card or anything else like that. And that'll be standard fare. You'll pull apart, you'll tag it, you'll put it into an ESD bag, and you'll put it wherever it needs to go. You want to take extra precaution on handling these LRUs because they're expensive and like the plane can't fly without them. So make sure that you are grounded while you're working on them. Make sure that the bag itself hole is nice and sealed so that way nothing can get into it, and it's properly tagged and labeled is essential for success whenever you're working with these sorts of components. All right, so let's say we wanted to remove an instrument, be it an analog instrument or a digital instrument, whatever. There's a couple of rules of thumb that we're going to follow. First off, we're always going to follow the maintenance manual. It'll have instructions in there to remove it in such a way so that way it comes out nice and safe and there is no issue. Once we have it off, there's a couple of things we're going to do immediately. We are going to be electrostatically grounded, and so that way, whenever we pull that instrument off, we're not like statically discharging the instrument and causing any kind of damage. Now, this is less of a concern with some of the older analog instruments, or maybe not a concern at all. However, just a good rule of thumb: anything avionics wise, anything instrument wise, you're working with, always have your ESD on because you never know. You might not be working on something that is ESD sensitive, but you might touch something while you're in there and cause the same effect. So, as just a general rule of thumb, always be grounded. You're going to take that instrument off. You're going to turn around and you're going to cap any of the cannon plugs that are there to keep dust, grime, any sort of damage from happening on the backside of it. Because remember, these are expensive, and we don't want to damage them. Then once you've done that, you're going to, if you have any pitot-static lines, you're going to cap those as well because you don't want to have any dust, dirt, water intrusion into it. And then you're going to tag everything. So you're going to make sure that the pitot-static line has a tag on it. You're going to make sure that the electrical lines will have a tag on it. Hey, look, this goes to the altimeter. It's cannon plug, such and such, whatever the thing is. So that way there can be no confusion on where it's supposed to go later on. And then we're going to place that altimeter, that instrument, or whatever it is that you're taking off. You're going to put it into an ESD bag and you're going to seal it up. Then you're going to tag it. And you're going to say, like, hey, look, this was removed per such and such a work order on this date by this person. And then you're going to go place it in wherever the holding facility is for those sorts of materials. You might be taking it back to your supply office because it's bad and they're going to place it into a crate and then send it off. Or maybe it needs to just go on the shelf or in some sort of holding area while you do other work. But those are the kind of steps and processes and procedures you'll follow for every single instrument that you pull off. You'll also then need to look at whenever you go to install it, you're going to do all that in reverse. You'll take it off, verify the tag, you verify that you have the right cannon plug and the right pitot-static line, all that good stuff. Reattach it, place it back on there while you're grounded, and then torque it down per the maintenance manual, and then put witness marks on there, little torque stripe, to make sure that the screws don't back off at a later date. However, then the next step with installations is that you're always going to want to see what follow-on maintenance is required per that instrument. Some instruments, won't require much of anything, if anything. However, some, like for instance, your altimeter, your airspeed indicator, will require a pitot-static check to make sure that everything is still good with the pitot-static system since you've disturbed it.
Other ones might have an MOC. If you were to take, let's say, like the screen off of a 737 Max and you were to reinstall it, it would have a system to where you would run a ops check on itself, and it would go through and it takes about 5 minutes where it brightens itself up and darkens itself down and does all the things to make sure everything works the way it's supposed to be. So always follow the maintenance manual on that because it will tell you what functional checks to do afterwards.